Hello. Interesting. Can you hear me like that, guys? Okay, awesome. Let's get started. We have a short session. We have a lot to discuss as well. So today in this talk, we will talk a little bit about the vision behind the reasonable Scala compiler. Just a little bit to get us started, and we will segue into the status. What we have, what are the numbers, so I guess this is why you're all here. Finally, we will talk about the architecture. So what makes our compiler fast, slow, the same? We'll answer these questions very soon. Before I begin, I would like to say the words of thanks, because a lot of people were indirectly involved in this project, inspired this project, and directly helped us out. We will start with Martin Odersky. So Martin Odersky, he wrote 2 compilers for Scala from scratch. That's pretty insane if you think about it. And yeah, we very much like this fact. Then Greg, my former colleague from EPFL, and then we collaborated with him while he was at Lightband. A year ago, he posted a very interesting article called The Limits of Scala Type Checking Speed. And there in that article, he said, well, look, guys, I've just hacked something up, and it turns out to be more than 1,000 times faster than the Scala type checker. Well, that was awesome. Yeah. And finally, Dennis, my former colleague from EPFL, he developed Scala native, and he showed that Scala applications can start really fast. So startup time is a common problem on the JVM, and with Scala native, we can say it's pretty much solved. So as you can see, these guys, they showed us that it is possible to have a very fast Scala compiler. And so that made our job very easy. So we just had to implement this. And so, one day I rushed into the office of my boss, David Keenan, who's the director of our department that does developer tools, and told him, look, David, I can compile Hello World super fast. Oh my God, this is going to be groundbreaking. And so this guy, he didn't show me the door, nothing like that. So this is how our project got started. So I'm very, very thankful to David. Then there's Shane. Shane joined us quite recently, our advanced Scala tools team, and he's already contributed major design and implementation modules in the new compiler. That's quite awesome. And of course, this project wouldn't have happened without a coordinated effort of a large team of people. As you can imagine, Twitter is a big company, so open sourcing these kind of things, it takes a lot of effort, and I'm very thankful that it's possible. I think that in a lot of companies that wouldn't have just happened. Like, doing some crazy greenfield work and then just making it available to the world. I'm really happy to see everyone here. Sasha, Remy, Julian, Richard. So thank you guys, really appreciate that. Okay, without further ado, let's talk a little bit about the reasonable Scala compiler. So clearly it's a Scala compiler, as you figured out from the name, but it has a very, very narrow focus. We only care about compilation speed, nothing else. So there are other compilers in the community, well, the Scala compiler, Dotty compiler, type level compiler, and a few others that have other focuses. But we only think about compilation speed. And we believe that it is possible to make Scala compilation faster, essentially by an order of magnitude on typical Scala code bases. And this is a very bold goal, and this is a research project. It's an experiment. But we think we're well on track. And soon we will show the numbers. Now, to get to this undertaking, this is quite challenging, right? Speed up Scala compilation by 10x. We had to set up some ground rules, some axioms, if you will. And the first rule was to rewrite everything from scratch. This sounds insane, obviously. But on the other hand, it's not such a bad idea. So while I was preparing for this talk, I went ahead and took a look at the code bases of Scala 2.12.4 and Dotty 0.40 RC1, the latest releases of the 2 major compilers for Scala. And as you can see, they're huge. So if we would want to do some fundamental experiments, like say change the representation of ASTs, this is basically a hopeless task in such a big code base. And we believe that by starting from scratch, we have unique possibilities to explore. Another ground rule is to start really small. So instead of, you can imagine, so here at Twitter we use Scala very intensely. We have millions of lines of code. So you would imagine that I would want to support parts of this code. as soon as possible. But we decided not to rush to implement a lot of features right away. And instead, we've come up with a small baseline of language features. We call this subset of Scala reasonable Scala. And this baseline, it will provide a solid foundation for our performance experiments. For instance, we would be able to add one single feature and then see how this affects entire compilation speed. And this is actually reasonable. This is not some pipe dream, because now we have this tool called Scala Fix, which can do automated code rewrites. So we believe that we will be able to use Scala Fix to downgrade normal Scala to reasonable Scala. And as a result, to be able to experiment on huge code bases and make our roadmap relevant. And so finally, this idea to start small, it had an unexpected benefit. In October, due to some reasons, more experimentation, we wrote almost the entire compiler. So in less than a month, we've been able to get started. This is pretty nice, I think. And so finally, this is something that a lot of people were worried about when a couple months ago we announced this project. We really do not intend to compete with Scala C or Dari. Instead, we view our compiler as a complementary effort. So there are teams at Lightband and at APFL hard at work pushing the boundaries of Scala. And it would be crazy to try to compete with them. As a result, we want to do our experiments in this small control setting and then provide insight that they will be able to integrate in their compilers if they decide to. So, if at some point, say Adrian from Lightband would steal our best ideas, I would be super happy. Oh my God, this is this is the best outcome for the project. All right, now let's talk about status. Enough of this preface. I've been talking about the implementation that we hacked up over October. So these are some line of code metrics. So here we count white space, we count comments, just like a few slides back. We did the same for Scala C and Dari. So our language model, as you can see, is pretty modest. 1,500 lines of code, and the majority of the compiler, it's actually parsing, which I found very surprising. So as you can see, more than half, about half of this number, of the total number, is tokenizer plus parser. And finally, again, the prototype of the type checker for this small subset of Scala that we chose is again pretty modest. It doesn't do much, but on the other hand, it already provides some foundation that we can build upon. Finally, something that may be surprising to you guys, for now we decided to leave CodeGen, production of JVM bytecode, out of scope. Because we believe that our performance experiments, they would be interesting even without that. So just type checking, it enables lots of things, including developer tools. As a case study, for the numbers that will be shown in just a couple of slides, we chose an implementation of read2, so fast implementation of regular expressions. It was done in Go, then it was ported to Java, and then it was ported to Scala within the Scala native project. So we just took this code, and it's 11K lines of code. It's not a hello world by far. It's non-trivial, but it's simple enough for our compiler to handle it. Why we find this corpus particularly interesting is that it provides an opportunity to directly compare our compilation speed with Java C. So there's a folklore saying that the Scala compiler is kind of 10 times slower than Java C. So let's see whether we can disprove this hypothesis or confirm it. OK, I know that you're really anxious for the numbers, but one more thing. I've been alluding to the fact that we just have a prototype of the compiler. So it's been hacked up during a month, so clearly you cannot implement the entire Scala in it. So it only supports a small subset of the language. It does not read the metadata. I don't know, it cannot read the signatures from jars. So we have to write stubs for that. And finally, it doesn't do type inference, so that advanced stuff that the Scala is famous for. OK, now I think we're really ready to see the numbers, given all these disclaimers. So first of all, our prototype turns out to be 20 times faster than Scala C. So these are hot numbers, which means that it's equivalent to running SBT constantly all the time. So as you can see, this 11K lines of code we can type check them in 33 milliseconds, which is about 300,000 lines of code per second, which I find pretty interesting. Really, when I was starting the project, I couldn't even believe that we would be able to do that. So clearly, all the disclaimers above still apply, but I think that's a pretty interesting result. Another point that I would like to make that thanks to Scala Native, so just like 5 or 10 minutes ago, I was thanking Dennis for his work. We've been able to improve cold startup time. So as a result, cold RSC, this is when you invoke SBT or when you invoke Scala C from the console without keeping it in memory. It's more than 10 times faster than cold Scala C. That's pretty impressive. And as you can see, at 300 milliseconds, it's not much. So the first time when I was testing that, when I wrote the first version of the type checker, I ran it, and it immediately finished execution. I was like, no way, this is going to be a bug. I mean, it doesn't do anything, but no, it really does stuff. So that's a pretty intense experience. And finally, I was talking about comparison with the Java compiler, and as you can see, again, all the disclaimers apply. RSC currently type checks read to S 2 times faster than Java C compiles read to J. So clearly, Java C does more work. But on the other hand, this shows that we can have comparable performance. Yes, please.
On the previous slide, didn't you just write that RSC doesn't do type checking? What's the RSC type check?
So what RSC type check means is that how much time it takes for RSC to type check this code base.
No, in your previous slide.
Oh, this one, where it says that code generation is out of scope.
Well, by type checking,
No,
before name resolution, you don't mean like
Here.
implicit search.
Yeah, that's right. So as I said, disclaimers do apply.
What is exactly being thrown out and what is exactly being
Okay, that's a very good question. What we're doing is just resolving names. So something that's required for producing executable code or for powering go to definition in IDEs. So we don't do type inference, we don't do implicit inference, this kind of stuff. All right, so this is it number-wise, and now let's talk architecture. Let's just go through a couple examples that show how tricky Scala type checking is. And let's see how Scala C, Dotty, and RSC handle this problem. Roughly speaking, you could say that type checking consists of 2 parts. First of all, you compute the signatures. For instance, for method foo, that it returns class foo, and for method b.c, that it returns c. And afterwards, you go through the bodies of the Scala programs and then use this information, the signatures that you've computed, to do name resolution and type checking, all the stuff that we've just been discussing. So for instance, during the second phase of the type checking, the compiler sees b.c, and then it remembers that it has a signature for b.c. Something like that. So this becomes trickier because Scala admits legal circle references between classes. So for instance, we can have a class A that returns something of type B, and we can have class B that returns something of type A. So it's not as easy as just ordering these classes in some lexicographic order or doing any kind of sort. You wouldn't go far just with that idea. Then the next step, there can be more and more complications, including inheritance. So what if we extend something? Now we need to resolve this name. We need to account for inherited members. What if we do wildcard imports? So this gets hairy very, very quickly. And we have the question, how do we order computation of these signatures and type checking of method bodies? So that's a big problem. What Scala C and Dotty does, they split this process into 2 parts. Something called a namer, which does signatures, and a typer, which does the type checking. And the trick here is that namer is lazy. So instead of computing signatures immediately after the corresponding method or value or type is discovered, Scala C and Dotty, they just create a lazy stub and move on. And afterwards, when the typer actually requests that signature, for instance, in our example, that would be when the typer goes to b.c, then the lazy completer triggers. And if we need to do more completions, for instance, to understand what the reference to class C means, well, so be it. Unfortunately, even though it's a nice trick, and Laziness is clearly one of the first pages in functional programming 101, it also has its downsides. Well, first of all, when everything's lazy, it's really hard to understand what's going on. So it's impossible to just take a look at the program and say, oh, it will be type checked in this order. As a result, debugging compilation performance, it's quite hard. So a lot of smart people have been doing that, and it's just hard. But the worst thing about this, about laziness, is that it makes it very hard to parallelize type checking. So laziness, it involves global mutable state. And as we all know, global mutable state does not work very well with multi-threading. Actually, I know this firsthand because back then at EPFL 3 or 4 years ago, we were trying to make runtime reflection thread safe. So we spent a couple months on that and then gave up. We just inserted a global lock. So clearly, that's not going to speed up Scala compilation. And so what we do in RSC, this is something we were inspired by the work of Greg Kosakowski in his Kentucky Mule project. We think that we figured out how to do a single eager pass over the code. So basically, as I mentioned before, it's really hard to order computations of signatures and type checking. And so Scala C kind of bails out. Dari does the same. But I think we have found a way how to compute this order and then follow up on it. And let's just have a really quick example where I'll explain the basics of the algorithm. And the details are available in the documentation. Again, we're looking at the same thing with a method foo that we need to type check, and with all those circular dependencies and all those complications. So here's how RSC will handle this. First of all, we do something called schedule. So it's not a phase, strictly speaking. It doesn't traverse all the trees. It traverses just parts of the trees. So the things that are highlighted in blue, they will be processed by schedule. So the compiler will discover the global definitions, and then it will somehow figure out in which order to process them. The next step is a phase called scope. This is where we handle circular references. So we believe that in order to make completers eager, we just need to handle circular references created by inheritance and imports. So as a result, these things that are marked in blue here, we process them and just them. And the rest we can do in parallel. So that's the wonders of this algorithm. And also something that Greg alluded to in Kentucky Mule. So the next step is called outline. This is where we compute outline types, which is an approximation of method signatures. So the things that I marked in red, they can actually be computed in parallel. So you can just go and spawn 4 threads. That would probably be very wasteful, because why do you spawn a thread? To just type check a single identifier, but you get an idea. So the previous steps, they build enough information for this to be possible. And finally, after all those signatures are computed, again, we have a lot of red. This is where we can do parallel type checking. And this is a major contribution of our work in RSC. All right, so this is, I understand this is a lot of hand waving, but on the other hand, I have just a couple minutes, or 1 minute. Oh my God, it's good that I'm almost there. So we're here at the final slide. To sum it up, what we've seen, we have a really fast type checker for a small subset of Scala. It's a prototype, so remember that disclaimer slide, but I think it already provides very interesting insights into Scala compilation performance. So if you click that link, you will not see anything, because it's all closed source. But I'm going to remedy that real quick. All right, that was fast. OK, enjoy. Thank you, guys.
All right, the next session is lunch, but I'm sure it's such a fascinating topic, we want a couple questions here.
Oh, yeah.
So you mentioned that your exponential subset of the normal cells. How much of your is 10 times speed up comes due to not doing that? Does the resolution things that take time which is actually due to what's the comparison there?
That's an amazing question, and this is what we will be figuring out in the near future. So what you see is the first version that works. We didn't do any micro optimizations or anything, but now that we have it, and it's about 5K lines of code, we can study it and answer the questions like this.
Let's thank Eugene and go on to lunch.